My name is James Lamb. I am a machine learning engineer at Spot Hero. We're a Chicago-based parking marketplace company. I am a maintainer on the LightGBM project from Microsoft Research, and I'm an adjunct instructor, at Marquette University in Milwaukee, where I teach Intro to R programming. And you may have seen my little South Park guy around Twitter and GitHub. Okay, so today I'm here to talk about sort of like esoteric topic in Python packaging. I hope you'll find it engaging. I'm here to try to convince you that extra files in your Python packages are bad and it's worth your time to remove them. Let's talk about it. Okay, so what is a Python package? I promised in the abstract for this talk that this would be brief. Let's see if that plays out. Okay, so when you look into the official sort of Python documentation on packaging, you are immediately hit with like, well, package means different things to different people. Let's break down that terminology. An import package in Python is a collection of Python files which are interrelated that you can sort of import like from each other. A collection of files like this. A Python distribution is a single file that's used to send an import package from one place to another. So when you use a package manager like pip or conda, and you're installing a package, that process is getting a distribution, like a tarball, a zip file, or something like that, from a place on the internet and bringing it down to wherever you are sort of doing your work. So this screenshot, for example, is from LightGBM's PyPI page, and you can see like there are multiple distributions for any one version of this library. A built distribution, of which wheel is one of and like maybe the most popular format, is something that can be used immediately. Installing that just means getting the files, putting them in a place on your laptop that Python will recognize them, and you are like ready to run. So for example, in the LightGBM project, we have a Python interface to a like moderate size C++ library. Our wheels will not have any C or C++ code in them. Instead, they'll just have liblightgbm.so or like .dll on Windows, and that's just a library that's like ready to use as soon as it's installed. In contrast, a source distribution is a file that contains sort of like all of the source code of your project, but nothing has been compiled yet. So when you, for example, go to PyPI with pip install, if there isn't already a built distribution for your platform, your Python interpreter, like all of the variables that go into that, you'll get a source distribution. And what will happen when you install that package is not just getting files from the internet and putting them on your computer, but then also maybe like building them. So what does building mean? For example, in LightGBM, we ship all of this C and C++ code. We ship this like setup.py file, which is using setup tools. And what's going to happen there is Python is going to be looking for a C++ compiler. It's going to be looking for the CMake build tool, and it's going to actually compile liblightgbm on your laptop before you can use the Python package. Okay, so in any type of distribution, I'd expect to find a couple things. I'd expect to find Python code in there. I'd expect to find maybe some like text files, like a license, a README, like maybe something like that. And for a wide range of packages, I'd expect to find package data. Package data meaning other non-Python and sort of like non-compiled object files that are included explicitly and intentionally. So for example, Django is an ecosystem of libraries for building web applications. The main Django library ships with a bunch of HTML templates in it for things like 404 pages, info pages, and like that sort of makes sense for the way that that package functions. In a source distribution, I'd expect to find some of these files, and I'd only expect to find these in a source distribution. These are the things that are needed to compile code. So that's like C, C++, Rust, Fortran source code. That's maybe like build scripts for like Bazel, CMake, autoconf, stuff like that. Maybe it's some other sort of like configuration files, stuff like that. Your setup.py, your setup.cfg. These are the things that Python needs to actually like build the package once the files have been downloaded to your machine. I'd only expect these in a source distribution. In a built distribution, that's the only place that I'd expect to find, say, a DLL, a dylib, an SO, some of these sort of already compiled libraries and object files. I wouldn't expect to find those in a source distribution. All right, I think that is like enough Python packaging 101. Let me start really like whining about things that I've seen on the internet. What are the implications of a larger distribution? So this is the part where after this, I hope you'll all be convinced that you should care about every single file that goes into the distributions that you push to package managers. One thing that I really want to be sure we clarify, and I see people like making this mistake a lot in discussions about package size on GitHub. There are sort of two relevant distribution sizes for Python packages. Honestly, for packages in any language. That's the compressed size and the uncompressed size. So when you upload wheels, you upload like tarballs and zip files to PyPI, the size that matters there is the compressed size, right? That's already been sort of like all your files for your project have been smushed together into one archive, and that's the file that's like traveling back and forth over the internet. The uncompressed size is sort of the disk footprint of all of the files in that archive once the archive has been unpacked. So for example, if you go poke around the site packages folder on like wherever you run Python, you're going to be seeing sort of uncompressed files there, right? You're going to be seeing the individual Python scripts and like all the other stuff there. So I wrote like a bunch of truly disgusting shell scripts to automate sort of building a table like this in preparation for this talk. Here's a couple of sort of like the most recent releases of some of these popular packages that you've seen mentioned in other talks here. And you can kind of get a sense of like the difference between the compressed and uncompressed size of their different distributions. Okay, so what are some of the implications of having unnecessary files in your distributions and larger distributions? Well, first, increase storage footprint for repositories like PyPI. So PyPI uses Google Cloud Storage. It's switched to that like in the last year or two, I believe, from Amazon S3. But either way, every time you upload a bunch of wheels and other distributions to PyPI, they have to store them somewhere. That costs them money. That is just like sort of the economics of cloud storage is that storage is a variable cost. So the bigger the things are, the more data you're storing, the more money it costs that service to run. Having larger files also means an increased risk of hitting sort of like service limits from cloud providers like Google on the number of writes. You know, if some of those files have to be broken into multi-part uploads, on the total amount of stuff you have there, things like that. And then having larger files for storage means that it takes longer to recover from, like to roll back to, say, a previous snapshot of files if you find some sort of like corruption of the contents of the index or something like that. Okay, larger files lead to increased outbound data transfer for package repositories like PyPI. So the way that PyPI works is when you upload your packages, they're stored in Google Cloud Storage. But when people run pip install pandas or whatever, they're usually not being served directly from that storage. They're usually being served from a CDN. A CDN is a content delivery network. That is sort of like a network of servers all over the world that are intended to basically like answer those requests faster by giving you an answer from a server that's physically located close to where you are. Every single time an installation request goes to a repository like PyPI, they have to take the matching wheel or the matching tarball and either transfer it out of the CDN to where you are, or in some cases, if there's not a version like out in the CDN yet, all the way from PyPI's cloud storage to the CDN. Outbound data transfer, if you follow the sort of like AWS influencers on Twitter, you'll know outbound data transfer is one of the absolute killers in cloud cost. And outbound data transfer almost always in cloud services costs more than inbound data transfer. Okay, but inbound data transfer matters a lot here too. So for anyone installing your packages, larger distributions means more inbound data. In a cloud environment, you do also pay for inbound data transfer, especially like depending on how your networking stuff is set up. If you're working in an environment with sort of like not a very strong internet connection, you can get timeouts, installation failures. If you're competing with other processes for bandwidth, you can have sort of like side effects on those processes by downloading larger packages. When you're building container images or virtual machine images, having to process and sort of download larger files increases the time it takes those images to build. If you are installing packages on demand in your continuous integration jobs, having to pull larger packages may make those jobs take longer. You can see there's just more darkness the further we go down. Okay, what else? Larger distributions lead to an increased storage footprint for the place that your code runs. So let's say you're like, I don't care about PyPI, I don't care about Conda Forge, I just care about myself. This matters for your storage footprint too. For example, the whole sort of like journey that led me to this talk started about 1.5 years ago. I was trying to use SciPy, NumPy, scikit-learn, and LightGBM all in an AWS Lambda function. really, really difficult to do. These function as a service services like AWS Lambda and Google Cloud Function have limits on the size of other files that you can attach to your function environment. In AWS Lambda, it was 250 megabytes uncompressed then. It's still 250 megabytes today. I want to remind you, look at the sizes uncompressed of some of these wheels, right? Like scikit-learn, you're already at 113 megabytes. So, including extra files in your distributions can make it harder for people to use in those environments. It can lead to increased risk of out-of-disk issues. So in some environments, you have to explicitly provision your disk ahead of time. And if that fills up with packages, it can cause outages for your applications. It can cause extra cost if you have to automatically expand that disk, just all kinds of problems. And again, this can increase the built image size for virtual machine images and container images. Let's talk some more about that. Okay, so increased size for container images. Why is this a problem? This is a problem that I deal with every day in my day job, sort of working on data engineering and data science applications that run in containers in a service like Kubernetes. So larger images can lead to increased storage cost, right? Those images have to be stored somewhere. And usually that's both in an image repository, either a private one or a public one like Docker Hub, and in sort of local container registries, say like the one that's used in Kubernetes when you are Docker pulling a new image. You have an increased risk of hitting storage limits. I've actually been paged on call because applications ran out of disk because Docker images were taking up too much memory, or too much storage. That's a real thing, folks. Larger images lead to longer pull times. That means it takes longer for your application maybe to restart when you need to restart it, which is no fun. And then for organizations that are using security scanning tools, larger images means more content to scan, which can lead to sort of longer time for those scans to run, which can lead to longer times for you to deploy, whatever thing you're trying to deploy. Okay, and then there's just a long tail of other very weird portability issues. I think this is where my sort of roots in the R community are really showing. R is very, very sort of specific about portability. Removing unnecessary files can also possibly help you avoid those files triggering other types of portability problems. For example, different versions of the tar utility have different limitations on the maximum file name, file name length, right? So removing files, maybe you'll end up accidentally removing from your distribution some large files that would have triggered those types of problems. I have worked in lockdown sort of enterprise Windows types of environments where every download from the internet is scanned for sort of a set of predefined unsafe file types, including a bunch of extra files you don't care about anyway in your package, could lead to your package triggering one of those checks, which is no fun if the people using your package, say, work at a bank or at a large healthcare company. And there's a whole other range of sort of portability issues with file names and file contents. That's special characters in file names, limits on the depth of nesting in file paths, the use of non-ASCII characters, processing of spaces in file names. I mean, I hope you all can tell, I have seen some stuff. Okay, so that was my pitch that there's a bunch of problems with having sort of larger than necessary distributions of your Python packages. So let's just say, yeah, it looks like everyone agrees with me. That's great. So you all agree with me. What are we going to do about it? So the first thing that I recommend is exclude your tests and test data from your distributions to PyPI. It is just not necessary for them to be up there. Or if it is necessary, I would argue your library is probably an exceptional case. There are probably more elegant ways to do this than what I've suggested here. In the LightGBM project, we do this just by having our tests at a separate directory a level above our setup.py. And then, what setup.py doesn't know, doesn't hurt it. If you do feel that you need to ship tests with your package, if you really feel that you need to use something like PyPI as the way to get your tests into the hands of developers or for some reason, at least turn a careful eye to the size of your test data. So if you're testing, for example, things that are not size dependent, like for example, that type conversions work correctly or that the expected error message is raised when some property isn't met, look very carefully and say, could we accomplish the exact same rigor of testing with less data? Sometimes I see developers just sort of like bundling a CSV, Parquet file, pickle file, or something like that. That was just like the one they had when they were first testing a feature, and then just dropping that into the tests. It might be an opportunity for you all to reduce the size of the stuff you put in your tests a little bit. Next, exclude your testing and development configurations. I have seen, looking around the contents of packages on PyPI with these disgusting shell scripts I wrote, I've seen like Travis configs, GitHub Actions configs, pull request templates, prettier, pre-commit, like all of these config files, not really necessary for people using pip install to install your package. So I recommend like looking carefully and saying, does this thing really need to be in there? Okay, the next one, exclude your long-form documentation site. So of course, your documentation that people are going to view directly through sort of entry points in the public API of your package, keep those. Those are your doc strings. Those are your maybe interactive examples, like things like that. But I see a lot of projects that bundle their long-form documentation site. That's like their images for all their different like versions of their logo. That's sort of Sphinx files or like Markdown files or other things that are sort of long-form tutorials, things like that, frequently asked questions pages. I would be very surprised to learn that very many people rely on finding those things in their site packages directory instead of either going to the internet or maybe cloning the repo ahead of time if they're, say, like going to be in an environment with spotty access to internet. So consider removing your documentation sites from your distributions. Okay. And if we have time later, I might have a fun short story about that. Okay, if your project uses Git submodules, all of the same things that I said, consider applying those to submodules. So for example, in the LightGBM project, we use Eigen and Boost, and we include them as Git submodules. And when we originally brought in Eigen, and Boost actually, we were originally just basically shipping the entire contents of those repositories in our source distributions. Well, this wasn't great because there's a ton of stuff in those repositories that's totally unnecessary to use those libraries in LightGBM, like all of these CI configs, like documentation, like other things like that. So all of these sort of standards I've described for your own code, consider that once you, as my little cartoon here illustrates, once you start sort of vendoring in other libraries, that's becoming your responsibility what you do and don't distribute. Okay, so I've been telling you about excluding files and like what to do. What's the actual mechanism? How do you actually do this? For source distributions, the mechanism is the manifest.in file. So this documentation I've sort of taken directly from the Python packaging documentation. It shows sort of the ordered list of steps that are used when a source distribution is built with like Python setup.py sdist or something like that. And you can see at the very, very bottom that the last thing that's processed is a manifest.in file. Manifest.in file is a set of directives that say things like include, exclude, prune, graft, things that basically say bring these files in, kick these files out. For built distributions, so if you're shipping distributions that involve C, C++, Fortran, Rust, other compiled code, there are, for a wide range of compilers and for a wide range of languages, compiler flags that explicitly allow you to optimize for a smaller built library size. Now, some of those have trade-offs between, say, like runtime performance and library size, but others I think you can like pretty confidently, unambiguously use for Python distributions. So for example, with GCC, using strip all to strip out debug symbols can reduce the size of your sort of built objects. Those debug symbols, for the most part, tend to only be necessary when developing the project and not for the average person running, pip install my package. And if you go look at these issues, you'll see there's been an open issue for a while, a really interesting discussion I've been following on CI build wheel about whether or not this debug symbol stripping should just be the default behavior of CI build wheel. And there's reasons like for and against it being the default behavior. But if you go look at that issue, you'll see a bunch of others in projects you've heard present at this conference talking about how they individually chose to strip debug symbols. For example, I picked like a random one from scikit image, but there are many in there, psychopg2 and all kinds of things. Okay. Let me tell you a few more things. I hope that you're feeling convinced. I hope you're feeling like, yes, I'm going to go look through the packages that I maintain and get some files out of there. Let me give you a couple of other sort of closing thoughts. First of all, this stuff really does work, and it really doesn't take that much time for some of them. So About a year and a half ago, we cut 14 megabytes uncompressed out of LightGBM source distribution just with like a couple minutes of manifest.in fiddling. Remember this picture that I showed with all the like stuff from Boost and Eigen? We just cut all that stuff out with our manifest.in. It seriously was a couple minutes, and now every pip install LightGBM that doesn't match to a wheel is 14 megabytes smaller. So it really, like, you really can get a big payoff without a ton of development effort. The next thing I want to say is that this concern matters even more today, now that newer versions of the pip resolver may end up installing multiple versions of the same package. So I took this directly from the Python Packaging Authority's documentation. Maybe you all saw this over the last year and a half as you've upgraded pip. The pip resolver now is much stricter about dependency, sort of like making sure that it's resolving all of its dependency constraints strictly. And what that means sometimes is that it has to download multiple files and inspect them, like multiple versions of the same library, to find a consistent environment. So these changes, like cutting a couple megabytes here or there out of a distribution, they matter even more when it's possible that people using your project might be actually downloading like 5 or 10 releases of it when they build their environments. Next, I want to thank a couple of people for taking the time to write things on the internet that like really sent me down this path. I started down the path towards this talk, as I mentioned before, with my experience with AWS Lambda. But thanks to these blog posts by Jim Chris Harif and Uwe Korn, I learned like to think a lot about a lot of other interesting and weird ways that your environments where you're installing Python packages can have files in them that you don't need. And I really, really appreciate Dustin Ingram for all of the writing that he's been doing, sort of making public the way that the Python Packaging Authority works, and specifically the architecture of PyPI. It was super, super helpful for this talk. Okay, the last sort of point I want to make, and it I think works really well with previous talks I saw in the conference about the importance of static analyzers, is that I really feel that one of the most powerful mechanisms for controlling artifact contents in the R community has been this static analyzer called rcmd check. Maybe it's not fair to call it a static analyzer because it does also run your test, but the parts I'm talking about now are static. This tool is the thing that you have to use to get an R package uploaded to CRAN, which is like the sort of mainstream repository for R packages. And it will explicitly sort of reject packages that contain non-portable file paths, executable files that aren't supposed to be executable, files that are too large, files with unusual extensions, all kinds of things like this. I am a really, really big believer that having automation, having static analysis tools is sort of a much more effective way to change behavior than we all agree to do this thing types of conventions. And I would love to see a static analysis tool like this for Python projects. So if you know about such a project, please tell me about it. I could not find one and I don't know about it. And if no one tells me that there's one that exists, I may try creating one myself. I think it could be kind of fun. With that, thank you so much for your time. Thank you to SciPy for having me. This has been great. You can find all of the slides on my GitHub. You can contact me at Twitter or GitHub. And with that, I'd be happy to take a couple questions.
So the first question we have, can you explain why the uncompressed size can vary so widely between the wheel and tar versions of a package? I would have assumed the final output to disk should be the same.
Was the question, can you explain why the size of built and source distributions would be different?
Why the uncompressed size can vary between wheel and tar versions of a package?
How can the uncompressed size vary between wheel and source distribution? Yeah, great. Okay, so like I mentioned in these slides earlier, so let's talk about the difference between a wheel and source distribution. Okay, source distributions have to contain the source code that's used to build your library. So for example, the source distribution for a project using C would have like .c and .h files in it. The wheel doesn't need to have those things, right? Because the built library is sort of already in there. That is the way that those two distributions, because they have different files, having different files means different compression ratios and different sort of final sizes on disk. Does that answer the question?
Yeah,
okay.
I think so. Next question, how do you define uncompressed size for the source distros? Is it all the unpacked sources? which will be required during build time, compiled files, or everything together?
Okay, great question. How do you define uncompressed size? That is a great question. So I want to be clear. This table that I presented with the uncompressed size was prior to installation. So that's a really good point. This uncompressed size was literally like download the zip file, run unzip, and run du on the directory. So it's a really fair point that after installation, the actual disk footprint of the source distribution is even larger because you have all of these files plus the objects that are compiled from the from the contained code. So really good point.
Okay, so someone is asking, I'm guilty of storing data in my PyPI package. What is the best way to make that dynamically loadable? Do you, they still need that data to use the package. Where do they upload it instead?
Okay, so the question was about shipping data with packages. If we're not talking about test data, if I understand from the question that we're talking about something like the functionality in like the scikit-learn.datasets module, right? I'm not sure that it is avoidable to have it bundled in the package. I'm not sure, that for example, it would be a good user experience for your code to load that data like from the internet at runtime instead of being bundled in the package. Those are sort of choices on maintainability and portability that have to be made by maintainers. Most of the points I made in this talk about bundling data in your packages were about sort of test data, where it's not really like a user-facing concern that it be, easily available or like realistic size and content. Hope that helps.
In your quick and dirty PyPI survey process, did the worst offenders typically have documented build configurations we could make PRs against? This could be a fun sprint.
Okay, great question. I am so glad someone asked this. It could be a fun sprint. So I can tell you, I have actually looked at some of these projects before. They all are like very, very heavily used in the community. By the way, these projects, I just picked popular projects. I would never classify these as like offenders or worst offenders or anything like that. Across Python projects, there is a wide variety of build systems, but not like an infinite or unreasonable amount of variety. Yes, I think it can be a very fun and interesting way for beginners to contribute to some of these popular projects in sort of removing unnecessary files from some of these projects. I've had some success with that in LightGBM and XGBoost, but that's just because I work on LightGBM and I'm internet friends with the XGBoost people. If anyone is interested in making those sorts of contributions, please come talk to me. I definitely can give you some advice on presenting that to maintainers in a way that they might accept it.
Hey, I'm actually involved in kind of the Python packaging space. Help with some of the PAPs and such in the PyPI updates. And this is a really important talk. Really important to these kind of nitty gritty things can really make or break a project being downloadable by a lot of people, especially on restricted internet connections. Just a few little things to note to answer your question. There at the end, there are some tools out there that do that. Obviously, there's some very simple twine checks. There's Pyroma, which investigates, which I'm one of the maintainers of, that investigates the source artifacts. And there's also a tool with scikit-hep. They have some very good packaging documentation that I highly recommend you check out by Henry. He's actually helped very recently revise the Python packaging user guide that you so aptly referenced. And they actually have a tool that actually checks your repository and your artifacts. It basically investigates for a lot of packaging-related issues. And just as a note, and also I guess there is, as to a question, I'm curious, especially with a lot of downstream distributions like CondaForge and Linux distributions and other packaging ecosystems, how do you kind of reconcile the kind of question of, well, on one hand, you want to minimize the size of the SDIS as well as the wheels, but on the other hand, a lot of those downstreams really like being able to have the build files and be able to actually run the tests against their installed copy to actually verify that their copy of the package, that when they rebuild it, is actually performing as the original maintainer passes the original maintainer's tests. Thank you.
Yeah, thank you so much for all that. I really appreciate that. So the question was about there are downstream build systems that expect to be able to do their own builds of packages and then run those packages tests to sort of verify that they're correct. That's a great point. I don't know an easy way to reconcile those two things. I'm not super familiar with the workflow, for example, how things are packaged up for Content Forge. It's a really interesting concern. I think that definitely in this space, there are some things that are like pretty unambiguously don't need to be in some of these packages, like the CI configs and other things. For actual unit tests or other sort of like things that repackagers might need to use to verify a correct installation, I think that's a really powerful use case for including them in your distribution. So thank you so much. It's a great point.
Okay, I think last question here. How do you convey build dependencies and instructions for a source package? For example, we ship compiled JavaScript with packages. How do we say that the source package needs Node.js to turn it into a usable package?
Okay, so the question is like, I have a package that relies on something that is not a Python package, like Node.js, maybe a particular version of Node.js. How do I indicate that requirement? I think that is actually outside of the scope of this talk and not something that I'm super familiar with. I'll tell you, for example, in LightGBM, we rely on the CMake build system for our source distribution, and we don't have like a particularly elegant way of handling that. We basically just check if there's CMake on the path and try to fail with an informative error if it isn't there. I'm sure that there has been significant work done on declaring those types of sort of non-Python dependencies. It's not something I'm very familiar with or that I looked at for this talk.